Hey, I'm Saim. My teammates are Chris and Steve, and we've been working on drawing on arbitrary surfaces using operation space control.
So, what are some of the applications of operation space control? Typically, with large robotic arms, they're capable of moving very fast and they have very high inertia, which means that they carry a lot of energy when they move. That's bad if you're trying to interact with the environment because they're capable of applying really large forces that you might not intend. Operation space control allows us to more effectively control the force our robot is applying to the environment, which will be particularly useful for delicate operations or for, in our case, drawing on a surface. At the heart of our system here, we have an operation space controller, which is taking in a point cloud of the surface we're trying to draw on and also estimating the normals of that surface. The operation space controller takes those surface normals and rotates the end effector such that it's in line with those surface normals, as well as rotating our operation space control system parameters, our mass, our damping, and our spring constants. The output of this is the torque vector that goes to the EWA. Now, operation space control you can think of as imposing virtual dynamics at the end effector. We have a desired dynamics equation up here on the top, which would represent a 6 degree of freedom spring match dashpot system, written in terms of the state vector x, which is for position and orientation, while we actually have on the bottom dynamics written in terms of our generalized coordinates q, which is our joint angles. We want to find a tau motor such that we impose the desired dynamics at the end effector. When we're not in contact, the operation space controller is trying to align both the position and the orientation of the end effector given a desired pose. On the right, when we are in contact, we align our end effector to the surface normal, so that's how we control our orientation. And for translation, we draw an error vector from the end effector to the closest point on the z-axis of the desired pose, denoted as the vector e, and we feed that as the error in position to our operation space controller. However, that maps to a force F actuator here, and that is in the plane of the point of contact because our spring parameter in the z-axis in operation space is set to 0. Meanwhile, we inject an external force up here on the right that acts purely perpendicularly to the surface, allowing us to decouple our trajectory tracking and our force that we apply.
So this is an overview of the simulation setup. You can see the EWA robot with the pen welded onto its end link, as well as a bowl and 3 cameras surrounding the environment. The cameras take one snapshot of the point cloud of the environment before the EWA is added on, and that point cloud is further used to estimate the normal of the surface. And briefly explain, the way it works is that the point cloud is used and saved. It's saved and used to create a KD tree, where it is queried to get the k nearest neighbors, and the query point is the tip of the pen. We can then apply a principal component analysis that creates a covariant matrix. That matrix has the interesting properties that the eigenvector corresponding to the smallest eigenvalue is the normal.
So here we can see the EWA trying to draw an M. We can zoom in here. We can see how the end effector is rotating to meet the surface normal as it draws. And below we can see the trajectory it's trying to track, and you can see that it tracks it pretty well. It's pretty spot on.
By making the geometries visible, we can more closely inspect what's happening here. We see the end effector tip in green, and around it are the nearest highlighted points, which are being used to calculate the surface normal, which is what you see popping up from the point. At the bottom, we see the trajectory being followed. We also thought it would be interesting to see how much of a role perception actually plays and whether the normal estimation helps. So this is the case where we don't use the normal estimation, we purely rely on stiffness control, and it's still pretty good, but we do see it skips a bit in the beginning because it's not able to apply the forces in the right direction. Compared to the case with normal estimation, where it's basically perfect. This does, however, come at the cost of slower runtime.
In conclusion, the operational space control is a powerful tool for enabling contact. However, getting force feedback during the implementation was very challenging, and so we did not manage to implement that, but it still works very well. In addition, our solution allows arbitrary drawing on arbitrary surfaces, which is really nice. We only tested with two trajectories on one surface, and we would like to test on complex surfaces, more complex surfaces in drawings to evaluate the robustness.